efficiency. Different algorithms devised to solve the same problem often differ dramatically in their efficiency. These differences can be much more significant than differences due to hardware and software. As an example, we will see two algorithms for sorting. The first, known as insertion sort, takes time roughly equal to C1 n square to sort n items, where C1 is a constant that does not depend on n. That is, it takes time roughly proportional to n square. So basically, in insertion sort, the time taken is C1 n square, where C1 is constant. C1 is a constant that does not depend on n. Now in case of a merge sort, the time taken is, which is the time complexity, is C2 n log n, where log n stands for log n and C2 is another constant, where log n and C2 are both constants. Now if we compare the merge sort and insertion sort, the insertion sort typically has a smaller constant factor than merge sort, so that C1 is less than C2. So basically, when we do the comparison of both the sorting algorithms, C1 is less than C2. C1 and C2 are called as constant factors. Let's write insertion sorts running time as C1 n dot n and merge sorts running time as C2 n log n. Then we see that where insertion sort has a factor of n, n's running time merge sort has a factor of log n, which is much smaller. For example, when n equals to 1000, log n is approximately 10, and when n equals 1 million, log n is approximately 20. Although insertion sort usually runs faster than the merge sort for small input size, once the input size n becomes large enough, merge sort's advantages of log n versus n will more than compensate for the difference in constant factors. For example, when n equals 1000, log n equals 10, which is and when n equals 1 million, then log n is 20. Although insertion sort usually runs faster than merge sort for small input sizes, runs faster than merge sort. For small input sizes, for example, let us put a faster computer A, running insertion sort against a slower computer B, running merge sort. For example, we take two computers. First one is computer A, and second one is computer B. So computer 1 is running insertion sort computer B is running merge sort. They each merge sort an array of 10 million numbers. Although 10 million numbers might seem like a lot if the numbers are 8-byte integers, then the input copy is about 80 megabytes, which fits in the memory of even an inexpensive laptop computer many times over. Suppose that computer A executes 10 billion instructions per second and computer B executes only 10 million instructions per second, so that computer A is 1000 times faster than computer B in raw computing power. To make the difference even more dramatic, suppose that the world's craftiest programmer codes insertion sort in machine language for computer A, and the resulting code requires 2 n square instructions to sort n numbers. So the task is to sort 10 million numbers Although 10 million numbers might seem like a lot, if the numbers are 8-byte integers, then the input occupies about 80 megabytes, which fits in the memory of even an inexpensive laptop computer many times over. Suppose that computer A executes 10 billion instructions per second. Now we let that computer A executes 10 billion instructions per second faster than any single sequential computer at the time of this, and computer B executes only 10 million instructions per second, and computer B executes 10 million instructions per second. So that computer A is 1000 times faster than computer B. Computer A is faster than computer B, maybe 1000 times faster. To make the difference even more dramatic, suppose that the world's craftiest programmer codes insertion short in machine language for computer A, and the resulting code requires two n square instructions to sort n numbers. Suppose further that just an average programmer implements merge sort using a high level language with an inefficient compiler, with the resulting code taking 550 n log n instructions. To sort 10 million numbers, computer A takes now to sort 10 million instructions, computer A takes number of instructions divided by instructions per second. So which basically instructions gets cancelled and the second is left. So if we compute, we will get 20,000 seconds as the answer, which is more than 5.5 hours, which is more than 5.5 hours. Now if the instructions per second is less than this while computer B takes, like computer we will calculate this for computer B also. So when we calculate this, it will take 1163 seconds, so which is less than 20 minutes. Less than 20 minutes. So by using an algorithm whose running time grows more slowly, even with a poor compiler, computer B runs more than 17 times faster than computer A. Computer B runs more than 70 times faster than computer A. The advantages of merge sort is even more pronounced when we sort 100 million numbers, where insertion sort takes more 23 days. Merge sort takes under 4 hours in general as problem size increases. So does the relative advantage of merge sort. Algorithms and other technologies. The example above shows that we should consider algorithms like computer hardware as a technology. Total system performance depends on choosing efficient algorithms as much as on choosing fast hardware. So just as rapid advantages are being made in other computer technologies, they are being made in algorithms as well. You might wonder whether algorithms are truly that important on contemporary computers. Okay.